that on purpose, because I received a notice ahead of time, ahead of this meeting, that this would be a wonderful meeting to talk a little bit about our current president, our last year's president, and this year's brand new, shiny new president, Kim Hay. The International Astronomical Union, the Working Group on Small Bodies Nomenclature, has decided that it is fitting to name a minor planet for Kim Hay. So Kim's got herself an asteroid.
Wow.
To call her own. And I certainly expect everybody to get out there and try and image it. Okay, so I'm going to read the part in the bulletin under her name. So the designation is it's 1988 RV4. And it was discovered in 1988, September 1st, by I'm going to spell the name, Debehoggne at Lacilla, and it says 809. I'm not sure what that means. But here's the important part. Kimberly Dawn Hay is an enthusiastic observer, sunspot and meteor recorder, and sketch artist who has contributed to the American Meteor Society, AAVSO, American Lunar and Planetary Observers, and the RASC. She has won the RASC Service Award and the RASC Chilton Prize. So that looks pretty good. That looks darn nice, and I think that is I think that's terrific. Kim, had you received that bulletin? Had you seen that?
It's tough because I sort of by sort of on Monday night, I was online and somebody had popped something up in instant message and I didn't know what the hell they were talking about. And then all of a sudden we were conversing back and forth because that particular person also has a designation in their name. So we were told, we didn't know if we were supposed to know about it, so we didn't say anything. So for 3 days, we've been sitting here awestruck, dumbfounded, not really sure what's going on because it still hasn't sunk in. It's surreal, I'll be floating out there forever, star stuff. I'm star stuff out there forever. And I definitely would like to get a picture of this. However, I got to wait for it to come back from around the sun. It's just coming around the sun now. It's getting up by Mars. So it is, it's still phenomenal. And I know I want to thank everybody who had put this together, who got this going. This is just phenomenal. And now I can tell people it's just great. And I want to thank you all. And I know Peter Jedicke worked on this several years ago for a lot of people. And I've also been in contact with Don Town from Belleville. I know he was online. I don't know if he still is. But he had sent me emails and sent me pictures of where it was. And he and Dave Cotterill actually took out a member from their center, Greg List, who also has a designation. So this is just fantastic. Thank you. Thank you all so much. I'm going to start crying, but I can't because I'm online. So thank you all so much.
It's a very cool thing. Congratulations, Kim.
Thank you. Thank you so much.
So perhaps the other person that you alluded to is Roger Hill.
Yes.
Yeah. So Roger Hill has also has a designation, and his is 1989 PK, and it was discovered in 1989 at Palomar. So I will read his citation, even though it's unfortunate that Roger can't be here. Roger Hill has been a member of the Royal Astronomical Society of Canada, Hamilton Centre for decades, and served on the board for most of that time, including as president. He edited the monthly newsletter Orbit for decades and has been involved with a plethora of outreach activities, including a course for new observers in virtual astronomy. So that's Roger also is on that big board. People with asteroids. Maybe see a doctor about that. So Kim, in addition to Peter Jedicke, Rick Wagner also worked on that. So
Thank you, Rick.
Okay, so that's all I have to say.
Oh, thank you
speaks
again.
for itself.
That is awesome. That's great news. I'm still starstruck, but yeah, it'll take a while. So Rick, we better get that telescope working down there in California.
We'll see what we can do.
Awesome.
I'm
You know
just
what?
looking up to try and figure out where your asteroid is right now.
Just coming around from the sun.
Do you have any idea what the maximum magnitude on that would be?
They said it was about 16.
Yeah, about 16 to 19.
Definitely not visual in my telescope.
No.
Can somebody post in the chat the numbers for both of those asteroids, please?
Oh, I'll get on that.
Thank you very much.
Okay, Susan, now that you've dropped that bombshell on the stealth surprise, we are going to move on to Rick Wagner, who is our main speaker for tonight, and he's going to talk about noise.
Okay, we're just going to try figure out how to get this thing working. Nope, wrong one. There we go. Nope, another wrong one. Share screen. Desktop, share. All right, hopefully you can see image noise, not sound noise. So we all know what image noise looks like. Here's a fine example from one of my early days of imaging with the my 8-inch in Ottawa, an Able planetary nebula with too little data. So you can see the colored speckling everywhere is noise. Here's a much more recent example. This is the Galaxy Ngc 4395. I chose it because it comes up later on this evening as well. And you can see kind of blotchy spots in the background in the galaxy itself. And this is actually a kind of an interesting example because, of course, some of the blotchiness in the galaxy is actually noisiness of the galaxy itself. We're actually seeing unresolved stars clumping and so forth. So it makes the galaxy look somewhat less smooth than it might otherwise. So when we take a picture of the sky, I kind of like to think of it as multiple layers. The bottom layer is the bias. When we read out an image from the camera, the manufacturer puts a bias voltage on the output. So this is just a small voltage that keeps the signal up away from zero and to the analog to digital converter and so forth in your software. Basically, it just looks like an additional source of electrons or signal. In my case, it generally runs around 500 ADUs. So on top of that, we what's called the dark current. The dark current results from the thermal jostling of the atoms in the chip itself. And this causes an occasional electron to break free from one of the atoms. And those electrons get collected in the pixels and stored there. And then they get read out after the fact at the end of the image as well. The next layer on top of it is the sky. So we have light in the foreground of our target. We always call it the background, but much of it's in the foreground. Light pollution, air glow, zodiacal dust, etc. And then additionally, there's the true background, which is unresolved stars and galaxies in the distant universe. And they all add up to provide another signal that is also something we don't really want in our picture. And finally, on top of that, we get the actual photons from the target object impact on the camera and produce electrons. And that's the signal that we really want. So because none of these things is changing much as we take our pictures, basically we should be able to just subtract off the bias, the dark, and the sky's a little more difficult because it can change across the field. But the idea is basically we can just subtract those signals off, and what we end up with is a pure signal from our target, nothing else interfering, and we get high resolution, low noise, everything's smooth and beautiful. So after we've taken our image, or before we've taken the image, we have to find out what is the bias. We have to measure it. We have to measure the dark current. And so we take what's called the bias frame. So this is basically just a zero length, or as short as you can possibly take, a zero length exposure. So there's no light falling on the chip. This is just measuring the readout itself. So you can see that there's an awful lot of noise in this. It's not nice and smooth like you might expect, which is a little worrying. We can do a histogram of it, and you can see that it looks like your classic bell curve. It's also called a Gaussian. Now, if the image was perfectly smooth, what we would have, in this case, at a value of about 249. So across the bottom of the graph, what we have is the brightness value of a pixel, and then up the side is the number of times that brightness appears in the image. So we can see that the maximum frequency is around 249 is the peak. And as I say, if this was a perfectly smooth image, what we would end up with is just a perfectly straight peak at 249. There would be no spread here. So this spread is a little concerning. Why are some pixels lower than 249 and some are higher? Perhaps it's just because there's variation in the chip. The pixels in the chips do vary from each other. They're not all exactly identical. So maybe that's what we're looking at. So we could check that if we take two bias frames and subtract one from the other, hopefully we should end up with exactly 0. But we don't. If we subtract one bias from the other bias, we get something that looks even worse than a single bias. So that means that what we're looking at is actually variation from one bias frame to another. So this is the noise that we're talking about. If we look at the histogram, you can see, well, it's harder to see here. We'll go to the next one. Here you can see the histogram in blue is for the single bias frame. And the histogram in red is after we've subtracted one bias from the other. And you can see the noise has actually gotten worse. The peak is broader and shorter, whereas what we're hoping to do is make it taller and narrower. And the reason for this is that when you combine two images, either adding them together or subtracting one from the other, the noise always adds. It doesn't, you can't subtract the noise off because we don't know what the noise is in one image or the other. All we can do is subtract off the average. My computer is not moving. Oh, there we go. So here's a more realistic looking graph. This is actually synthetic data. So what I've done is chosen a signal level, 500 ADUs for the bias, 670 for the dark current. The sky, I think, was at 50, and the target is at 1000. And then what I've done is I've added a Gaussian error term to each pixel. So I should clarify here, this graph shows 100 pixels. So we can either look at this in one of two ways. One is, this is like a string of 100 pixels across a single image, and we're looking at variation across the image, presumably a featureless area of the image. Or we can think of picking one pixel out of a series of 100 images, all perfectly guided and all exactly the same exposure, etc. We can take that one pixel and see how it varies from image to image. And what you can see is that there's a lot of variation. The variation in the bias is called the read noise. And the read noise is very interesting because it's a different physical process than our other noise sources. It's just variation on top of the bias voltage. And generally, when you get a camera, it will tell you that the read noise is 9 electrons or something around there, usually around 9, 10 electrons if it's a CCD camera. CMOS cameras, the read gain can actually vary, but it's usually much smaller, anywhere down to a few electrons. Come on, wakey, wakey. There we go. Okay, so what I did here, and we'll start this again, is this is 6 different bias frames that I've connected together in a little. And you can see that there's quite a lot of variation between them all. There are also a few pixels that are consistently slightly higher than the average or slightly lower than the average. And those are, in fact, pixels that do vary from their neighbors. So they're sort of outliers. And we also have a dark frame, which you can also see has noise in it. And here's the histogram for the dark frame. You can see that most of the pixels are fairly low values, down below 50. But there are some pixels getting up above 100, even 150. So those are hot pixels that we have to deal with. So if we can't just subtract a bias frame from our image without increasing the noise level, we have to find some way to measure the average bias. And the best way to do that is to take a whole bunch of bias frames and average them all together. So that means just a whole collection of exposures of 0 length, and we just average them all together. So this picture is an average of the 6 bias frames that I showed earlier. And you can see that it looks much smoother than the individual bias frames. So what it means is essentially the more bias frames we take, the closer we get to measuring the actual signal in the bias, as opposed to the noise in the bias. We can subtract that signal off of our image, and what is left behind is only the noise that was in the bias that was part of the original image. So that bottom layer of our target picture, the bottom layer is the bias frame or the bias signal with noise on it. And by having a good average bias, we can subtract out that layer and only leave the noise from the bottom layer. And we can do the same thing with the dark frame. The dark frames are a little less convenient because they have to be of the same duration or longer as your exposures. So if you're shooting 300-second or 400-second pictures, you have to take 9, 12, 20, 30, 50 dark frames of the same duration. So once we've averaged all those together, we can subtract the bias, we can subtract the average dark, and what we end up with is our picture with the target signal, the sky signal, plus the bias noise and the dark noise. And that's the best we can do, unfortunately. So if you look at my article in the recent Regulus, I go into more detail. Some of the adding noise, how noise adds together, because it doesn't just add, you actually add the square of the noises and then take the square root. But if anybody has any questions, I would be pleased to answer.
I have a question.
Okay.
So a dark frame is, you obtain a dark frame by having like your lens cap on, say, right?
Yes, and the shutter closed.
The shutter
And it should be done in the dark too. A lot of cameras actually have light leaks. So you might think that with your lens cap on and your camera and your shutter closed, that you would be able to do them in the afternoon, which would be very convenient. But in fact, a lot of cameras have light leaks and it won't work.
So how do you obtain a bias frame?
Bias is basically the same thing as a dark frame, except that it's of 0 duration. Now, if you're shooting a CCD camera, you can actually tell your software to take a bias frame. And basically what it does is it cleans the chip, it empties the chip, right, in preparation for a new exposure, and then instantly reads the chip out again. So there's no time for dark current to take effect. There's no light on it. So all you're reading is the actual electronics essentially. And that's what gives you your bias level and your read noise.
It's
So the
temp-
basic difference between the two is exposure versus no exposure.
Yes.
Okay.
Is temperature a factor, Rick? Do you have to take those at the same temperature that you are taking your pictures at, or can you just
Yes.
take any temperature?
Yeah, they should be done at the same temperature. So
Okay.
if you have most of the CMOS, well, most of the cooled CMOS cameras and CCD cameras have thermoelectric coolers and temperature sensors, and they will actually maintain a consistent temperature. If you're shooting with cheaper CMOS cameras or DSLRs, you're better to try to shoot your dark frames around the time that you shoot your light images, so
Right.
that the camera is at roughly the same temperature.
What about bias though? The bias shots should be at the same temperature as well, or?
The bias probably doesn't matter, at least to the first order. The ambient temperature, the outdoor temperature, affects the electronics in the camera. And there are some people who suggest that if you are taking bias frames, you should actually take them at the same outdoor temperature as your science images are taken. But I've never noticed an effect. So the interesting thing with the darks is that if you cool the camera, of course, there's a lot less jittering of the atoms in the chip. And so there are less, the dark current is less. And if for every 6 degrees Celsius that you drop the temperature of the camera, the dark current drops by 50%. So you can see that if you're trying to measure the dark current, you want to be at, pretty close to the same temperature. If it changes a few degrees, you're not measuring the same dark current. Anything else? I will try to come up with a talk on how we balance the noise sources. One thing that a lot of people do, you see people running their cameras at -40 to try and reduce the dark current. And in fact, what it ends up doing is your dark current noise is way smaller than the other noise sources in your image. So it doesn't make any difference at all. Running at -20, -30, -40, there's essentially no dark noise left to worry about. So the idea is that you can balance the temperature you're running at, the sky conditions, the filters you use, how many sub-exposures you do, and so forth, to try and sort of equalize all the noise sources and keep them all reasonably low. It's kind of like putting in very, very expensive thermal windows in your house and not insulating the attic. You want to spread your effort around so that your noise sources are all more or less comparable with each other.
I had a question.
Sure.
So if you're when you're talking about subtracting the dark from the regular, is that using one of the stacker programs, or what happens if you're just taking individual shots?
If you're just taking individual shots, there's not I guess there's not a lot you can do. I'm not sure how many of like your regular sort of picture processing softwares like Photoshop and GIMP and photo elements and stuff. I don't know how many of those will actually allow you to subtract one image from another. But certainly the stacking software, you can, for instance, with your DSLR, the pictures you're taking, Bruce, you could take, put your camera on the tripod, take 10 pictures of the sky, right? You do them fairly quickly so that things don't move too far.
Right.
And then put your lens cap on and take 10 pictures of the same duration, right?
Yeah.
And then you go to a stacking program like Deep Sky Stacker or something.
Yeah.
And you hand it your light pictures, in other words, your sky pictures, and you hand it your dark pictures, and it will take all the darks and combine them all together and subtract them from all your sky pictures.
Okay.
And you stack your sky pictures. And what it does is it will get rid of all I don't know if you've noticed, but on some pictures, a lot of DSLRs, you get little bright red and green, blue pixels.
Yeah.
And doing the dark frames will remove that.
Okay. Yeah. Okay. Yeah, I've noticed a couple of background pixels. Yeah. So okay. Well, thanks very much. I'm going to give that a try.
Hi, Richard. It's Dean.
Hi, Dean.
In that same Deep Sky Tracker program, I see there's these dark flat files. I guess they're not noise. Like you didn't really talk about those. So there's some other sort of interference or some sort of distortion.
The flat darks are the same thing that I've been talking about. You think of your flat frame as something you're measuring, and there's going to be dark current in it, and there's going to be noise on that dark current, and you would like to get rid of that. So you take what's called a flat dark. So it's a dark frame to match your flat frames. Now the flat frame is also subject to noise and so forth, but it's a different part of the image processing process. Your camera or your camera lens, your telescope, etc., probably doesn't illuminate the chip perfectly uniform. When you take a photograph, say through a telescope, you might notice that the corners are darker than the middle of the frame. People call it vignetting. Especially like you take a picture of the blue sky with a wide angle lens, you'll see that the corners are noticeably dimmer than the center of the frame. So what that means is the corners are getting less light from the lens than the center is. And also, I mentioned that pixels are not all identical. Some of them are more sensitive and some of them are less sensitive than the average. And so they respond more or less to a certain amount of incoming light. So you take a flat is basically a picture of a perfectly uniform light source. And if you then divide your image by that flat, what happens is your picture of the stars is too dim in the corner, but so is the flat too dim in the corner. And so when you divide the two, it corrects for the vignetting, and it also corrects for all the intrapixel variation in the chip. So it just gives you a much smoother and more uniform picture. And where that really comes in handy is particularly when you're stretching an image a long ways, you'll find the corners get very dark. But also if you want to subtract off the background sky, because I didn't talk about removing the sky, you have to get whole frame evenly illuminated to be able to figure out what the sky background is, and then you could subtract that. So yeah, the flats are are also a source of noise, but it's at a different stage in the imaging process.
Thank you.
One further question about the flats, because flats deal with the vignetting issue.
Yes,
Do you use flats when you run photometry for your variables?
all the time.
All the time,
Absolutely
okay.
critical.
Yeah, yeah.
Because for
Okay.
instance, if your comparison stars are further out from the center of the frame, so
Yeah.
vignetting that you wouldn't even notice, can be 1 or 2% quite easily, and it's going to affect the relative brightnesses of stars in the frame.
Thanks.
Hey, Rick, what do you use to get your flats? And I've heard people use pillowcases over top of their optical tube. Is that doable or?
Yeah, a lot of people, yeah, or a t-shirt. One thing I'm a little suspicious of is woven fabrics. And I'm not sure it's an issue, but I made, for the Boltwood scope, I made an aluminum frame and then I covered it with a piece of sheet. And so it fits over the top of the telescope. And basically it reduces any variation across the frame. But I noticed that the flats I get are not exactly the same as the flats that I get other ways. And I'm wondering if, because it's woven, it's almost like a diffraction grating. So you're getting, some tendency towards spikes, like you can imagine if there was a star bright enough to shine through there, you'd have spikes from the threads. They're basically thousands of spider veins, right? And so I think that may have an effect. So if you're going to do it, use like a knit fabric, like a t-shirt. I actually just use the twilight sky. Starting a few minutes after sunset, I point the telescope just off of vertical. So you point it exactly vertical, but then 5 degrees away from the direction of the sun. And then I just shoot pictures. And I do anywhere from 12 to 20 pictures with each filter.
Okay.
And the trouble with that is that you do get stars show up in the flats. And so then you have to use like a median filter on the stack. So you don't average all the images together. You actually take sort of it's called the median. So it's like the middle value. Each pixel, it looks at all the images and says, oh, well, this pixel is way too bright compared to all the rest, probably because there was a star there. And so it throws that one out. And all you get is essentially the starless portions of the frame. So the other option is to make like a flat box. You can use styrofoam. That's what I did with my old telescope, was made a cardboard box with a couple of pieces of frosted plastic and then a bunch of LEDs in the back. And then you put that over the front. And that has the advantage that then you can do it during the day. The twilight flats or a t-shirt flat, you basically, you pretty much have to do it during the right time at twilight. If I'm 10 minutes late starting my flats, it's already too dark in the evening and I've missed my chance. So it's convenient if you have a light box or a, they also make things called flat, what do they call, flat panels? And they're like an electroluminescent panel, and it's just a rectangular panel that just glows gently. And then you can put that over the aperture of your telescope. The trouble is once you start getting into decent sized telescopes, like 12 inches and 16 inches, they start running for $600, $700, $800. So I haven't done that. I can talk more about flats some other time.
It's helpful.
Yeah, my main interest here was kind of to follow up on what I wrote in Regulus, because a lot of times you hear people talk about the dark noise, when what they really mean is the dark signal, but it's a dark signal that has noise on it. Same as your star picture, your galaxy, whatever. When you're imaging, you kind of think of there's photons coming in, and there's 1,000 photons a second after second for hours and hours, but it isn't really. It's 1,000 photons per second on average, but this second there might be 900, next second there might be 1,050, and so forth. And so when you take a picture, you don't necessarily average out to exactly 1,000 photons per second over the whole exposure. You're going to be a little bit higher, a little bit lower, just randomly. And that's the noise that appears in every signal you get. Your bias, your dark, your sky, and your target all are subject to noise that are sort of variations on the signal. And it's the noise that trips us up.
I've got a question, Rick.
Yeah.
In music, when you're recording music and you want to eliminate noise, there's a plugin called Dolby, which has made a fortune selling their plugins. Has anybody invented any kind of plugin to automatically remove noise from visual photography?
I've never heard of one. Yeah, I don't know how the audio ones work. I mean, it's an interesting analogy between audio and our imaging. You think of noise when, for instance, a classic example, go to the brew pub in Smiths Falls, and the noise level there is absolutely oppressive. I don't think I've anywhere ever been in a noisier place than that. And you can't make yourself heard to the person across the table from you at all. But it's not what we think of as noise that's the problem. If that sound level in the room was exactly the same, but it was a constant 440 hertz sine wave, then it's a pure signal. We would be able to easily distinguish another person's voice and understand what people are saying, because it's all signal, there's no noise. The noise in the room is the variation in the signals, and that's where our speech gets lost, is in the variation in the sound in the room, the noise in the sound, as opposed to the sound itself. Now, the only thing I can think of is that Dolby is, they have a fairly good idea of what the signal is going to look like. An audio signal is a fairly well-defined, frequency range and so forth, and probably has fairly common noise sources, like tape hiss and stuff like that, that they can focus their routines on. That's the only thing I can think of. All right, thank you very much.
Thank you. There's no more questions for Rick, which was an excellent presentation. Next, we have Hank Bartlett and Hank's Sunspot.
Okay, and just before I jump into that, Rick, this is purely a compliment. This talk has reminded me of the night going to the London GA Observatory and back with you on the school bus. And it amazes me the amount of knowledge you have. By the time we got back, I think I maybe started to understand a little bit of Greek. And although I don't retain it, you can make your thoughts understood and put it simple But that is an amazing amount of work to do to get images and everything. That's just absolutely blows my mind when I just go out and point and shoot and that's it. And, you know, maybe I imagine, you know, the images would be better if I did all those kind of things. But just thanks. That was awesome.
Oh, you're welcome. Thanks.
Okay. So we're going to share a screen here for Hank's sunspot. And we're going to share this one, I believe. And slideshow. And do we have a full screen there?
You are good. Single slide, full screen.
Okay, because mine has a green box on it, but maybe that'll go away on the next slide. Anyway, the last month since October 14th to November 10th today, solar has been, you know, picking up, getting better. Weather has been not so good, especially in the first part of October before the last meeting. It started to pick up now in the latter part of October, but it was very, very hazy, which really affects the images. This image in the center here, I picked because it was one of the few that was not affected by a lot of haze and moisture in the air.
Okay, sorry, Hank, I'm gonna have to stop you. Is there 3 images on your slide? Because we only see 1.5.
Oh, see
It
there.
goes
Oh,
Hank's sunspot,
okay.
October 14,
Yeah,
and then that's it.
that's where that green box probably is. Hang on a
Okay,
second
so
here.
just-
We'll just-
Yep, stop share and reshare.
Okay. I'm going to. Oh no, I can't get it to go. Okay, there. Got that away. Hang on. And let's make this full size. Go this now and do share. We'll get this one day, Kevin. You know, we'll get it figured out, us guys that
And
aren't.
then the minute that you do, we'll add a second display onto your system, and that'll mess up the whole thing again.
Let's try this and
Okay, now we're
do
seeing the
slide-
whole window of PowerPoint of
and now we'll
LibreOffice.
do slideshow.
And now
And
we're
now we should have
seeing,
3 images.
yes, we are.
Okay,
Go
perfect.
ahead.
Okay, so blah, 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 all I said. Okay. This image was picked because it wasn't so affected by haze, and the moisture in the air really can mess things up, being hydrogen, of course, and you're imaging hydrogen. The image on either side are the 2 M flares from October 28th. There was 4 flares very quickly in that time. The gong managed to catch 2 of them. The one on the 29th, the morning of the 29th, none of the cameras caught it. And I, of course, didn't catch it either because it was off hours and we had cloudy weather. But as you see, these flares on the left and the right are face on. That's something going to be for later on. When you see a flare face on, you get a bright glow. You get a really bright, if it's an X flare, you get a lot of white out and everything. And that's about all you see. An M flare that just went on, what was it, yesterday? Yeah. Shows a different story. So now, overall solar activity is on the rise. It's on the rise in the amount of spots. It's on the rise with the activity within them. Since the last meeting, the sun has generated 1 X class flare, 8 M class flares, and 76 C class flares. That's a lot. When a few months back, we were getting like 20 C class flares, or maybe 30. So it's a very satisfying month, with the exception of October 16th, 17th being spotless. And you can see here the graph, the X-ray graph on the 17th, it's going down, down, down back into that terrible minus 10 to the minus 7, 7.5, 7.6 region. Even though on the 18th, new sunspot 12886 came around on the eastern limb, you can see here that it still tended to drop for the next day, almost entirely, half the day at least, before it started to pick up and rise again on the 20th and get back up into some decent activity in higher B flares, and possibly, build us some interesting observations. Why it lagged, it's purely inactivity within the spot, but it took a little time for things to get coming interesting again. So it was 4 kind of blah days there, except for the nice sunspot. Then on the 28th, 29th, however, the sun brought us 4 flares in, so I got to move this little bar here out of the way. There we go. Above C-class level in just 19 hours. And that was the 3 M's and the 1X. The X is the gong H insert on the below the graph, lower half of the graph. And you can see the immense amount of white flare there because it's a monochrome image. And it looks dazzling. It looks fantastic compared to what you normally see on the sun. Very eye-catching, very exciting to get. And this, of course, generated and propelled us into this, there's going to be a huge aurora storm. I hear rumors people even drove to the Sioux. He's not here tonight. And yeah, we're going to catch this aurora. It's going to be fantastic. And it fizzled right out. And it was basically nothing. And then, to add insult to injury, we missed out on what much of North America saw and much of the world, the November 3rd, as a result of the November 1st area active region 12887 M1 eruption. So we seem to be entirely in an aurora black hole around here. This is my best shot of aurora on that night of November 3rd, and it doesn't show well here at all, but there is a pinkish glow on the horizon, and there was a green band above that, and that was at 1615 seconds, and there was just about nothing. It was very sad, very unfortunate. A lot of people, Rosemarie especially, were really psyched up for this, and Malcolm. And now just a couple of images. This is from November 1st. From November 1st to now, I've almost had, most of all the observing I had in the entire of October. And it's been good. It's been clean and clear more. You can see the clarity in the left-hand side, no granularity from the hydrogen, the haze in the sky. And very happy with this. And the amount now, obviously the plage has been brightened here. Maybe not so much on the left, more on the right. I kind of overdid the right-hand side, I got to admit. But to be able to see the plage on nice, new, big, active spots coming around is fantastic. It's very, makes you expectant of really good activity coming up. And this on the 8th was very good as well. Good sunspot matches to the H alpha. Sometimes the sunspots do not show up very well in the H alpha when you have it tuned to the proms and the lesser surface, or should say more active surface bright spots in that. The spots themselves tend to disappear. Now, this was on the 9th, which is just yesterday, and the sunspot 12891 erupted with an M flare after going around the limb. Now, I said earlier about the flares when they're face on, the nice bright white and everything else. But this is what happens when there's a flare and you don't see any of this. you can see at the top of all these little crescent edges, limbs of the sun. Now, on the left-hand side, the black and white, the monochrome image, is the sun exactly at the time of the eruption at 1702 from Cerro Tololo, Chile. And there is no evidence really at all of there being any kind of eruption because it's just around the limb. But then as 10 minute by 10 minute by 10 minute went on, it grew and grew and grew. Now, it did not cast out into space as much as some of them do, but you can see the color image on the left, which I brought down from spaceweather.com, showing the rings and rings and loops and fantastic imagery that there was. And watch it across these images, all these images over 2 hours and 40 minutes. So when a spot is facing you, you miss all that. But when it's on the edges and there's an eruption, you get this fantastic pluming of prominence and everything. And unfortunately, missed this, cloudy, did not get any images at all. But when you do solar imaging, this is some of the joys of it. And that's all I have to say for this month.
Thank you, Hank. Awesome.
Thank you.
Great, Hank. Thanks. Did you get out today?
Yes, I did. I haven't processed those images yet. There wasn't an awful lot going on, but I hope to get some decent images out of it. The sky was good and clear and scene was fairly steady.
Mm-hmm. Yes, it was.
Did you get out?
I did.
Good. Wonderful.
I did get some pictures. I haven't even looked at them yet,
Okay.
but waiting for that rainy day to happen, you know.
I called that till 1 a.m. this morning. That's what I was doing. Another one.
It's a little too late. Okay, thank you. Well, next we have Rick Wagner with What's Up in the Sky for November. I know we have lots happening.
And just in case Rick doesn't know, he is muted.
Okay. Now, so RASC events and local events. Friday evening, late evening, the Sunshine Coast is presenting Margaret Ikapi, probing the epoch of reionization with the Simmons Observatory. It sounds like that should be fairly interesting. Doesn't start until 10 o'clock. On the 19th, I think that's next Friday, Larry Widrow from Queens talking about disequilibrium in the Milky Way. We all know that the Milky Way is a spiral galaxy, which normally would be in a plane, but it's actually got a warp in it. And so what he's going to talk about is some of the even smaller signs of disequilibrium in the motion of the stars of the Milky Way. And on the 20th of November, Roberto Abraham is going to be talking. I didn't get a topic for that one. I think this is the Mississauga Center, so it'll be online. And he's the fellow at U of T, I guess, who was one of the fellows who developed the Dragonfly array of telescopes and cameras that's doing the ultra low brightness imaging. I noticed the other day there is a new fast radio burst podcast on the Queen's University Observatory site called Dangerous Universe Star Slaying. So you can find that at their website. The British Astronomical Association on the 17th has a webinar about the Winchcombe meteorite. On the 3rd of December, the radio astronomy section is talking about Ceres Presents. And on the 4th of December is their Christmas meeting. AAVSO has some promising webinars coming up. On Saturday, David Turner from St. Mary's in Halifax. Hasn't given a topic yet, but I think he's big into Cepheids, so we can hope he's going to talk about something like that. And John Thorstensen talking about cataclysmic variables, also a very interesting topic, something that I do a little bit of. 27th of November, Christine Larson talking about getting started in solar observing, and another talk by Gabriel Moravsky to be announced. And on the 4th of December, Chris Colvin talking about AAVSO SLU. SLU is one of those commercial telescope, online telescope facilities where you can sign up and take pictures. So that'll be interesting. We're getting more and more night all the time as we approach the solstice. You can see by the 21st of November, we're up to over 11 hours of astronomical dark, and over 12 hours, almost 12 and a half hours of usable darkness after nautical twilight. Sun is definitely getting lower at noon. By the end of the month, it's only 23.5 degrees up in the sky. So I've noticed the shadows of the trees are falling on the deck when I'm trying to have lunch outdoors on the deck. Here's your lunar calendar. New moon was on Friday, first quarter on the 11th. So basically there's no evening observing for now for the next couple of weeks. So sky events, first quarter moon on the 11th, tomorrow. The 12th, the North Torrid meteor shower peaks. This is a very minor shower, fewer than 10 meteors per hour, and the moon will be a problem. 15th of November, Algol is at a minimum for 2 hours around 2:50 Eastern Standard Time in the morning. 17th of November, the Leonid meteor shower peaks. It's funny, I always think of the Leonid meteor shower as a pretty decent one, but it's actually only rated for 15 meteors per hour. And it's going to be right near a full moon, so we're not going to see much activity there. Also on the 17th, Algol is at minimum again at 10:40 in the evening. Full moon on the 19th. And not coincidentally, on the 19th, a nearly total lunar eclipse. This should be a very attractive one. It's 98% covered. So it'll be a very nice looking eclipse, and it's going to be situated right between the Pleiades and the Hyades. So it'll be very photogenic. The only unfortunate thing is it happens between 2 o'clock and 6 o'clock in the morning. And the 27th of November, we have last quarter moon. Then going into December, the 3rd of December, a very thin crescent moon just above the southeastern horizon shortly before sunrise. The new moon on the 4th. And on the 4th as well, Venus is at its greatest illuminated extent. It's getting to be quite a decent sized crescent now as it comes around towards inferior conjunction. The 5th to the 9th of December, a very photogenic set of pairings or groupings between the moon and Venus, Saturn, and Jupiter. Over those 4 nights, the moon starts down to the lower right of Venus, and then each evening it moves further and finally ends up to the left of Jupiter. I was out, probably 3 or 4 nights ago, and the moon was very attractive, sitting right between Venus and Saturn, and formed a nice line from Venus, the Moon, Saturn, and Jupiter along the ecliptic. And the 8th of December, the date of our next meeting, Algol will be at minimum for about 2 hours around midnight. I'm suspicious on the timing for that. I'll have to check. That might be not incorrect. Check your observer's handbook. Comet Leonard is showing some promise. I think Walter's already tried observing it. This is its path sort of from tonight on through early December. And you can see it starts out quite slowly, but then really cranks up, just tearing across the sky from night to night. What's really interesting is you can see it's just in the northern reaches of Coma Berenices. So it's going through galaxy territory. And if we look, we find one night it goes past NGC 4395, which is the galaxy that was the background for my last talk. You can see this is about a 1 degree wide field here. And then a few nights later, it goes right between 4631 and 4656. 4631 being, of course, the whale galaxy, and 4656 is the hockey stick. So that'll be, we can only hope that it's clear that morning, because that'll be a terrific picture. I've heard online that the comet's quite bright, up around 9th or 10th magnitude already, and going to be getting brighter. Asteroids this month, Ceres is at opposition on the 27th of November at magnitude 7, so you should be able to see it in binoculars. And it's kind of interesting because it is the only dwarf planet that you'll be able to see in small telescopes or even fairly large telescopes. The next brightest one, I think, is Pluto, which is now below 14th magnitude. So here's your chance to see a dwarf planet. On the 20th of November, 2407 Haug, a pulse star. The star is 10th magnitude, and the asteroid is 15th magnitude. So there's a 5 magnitude drop in brightness for a maximum of up to 2.2 seconds. And you can see here's the path, includes Kingston, Amherst View, Battersea, Elgin. Unfortunately, I'm outside the 1 Sigma path. Also makes it up the river. So almost everybody here's got a good reason to go out and watch this thing. And interestingly, the same night, a few hours later, 2826 Aughty is going to be occulting a star. Now this one is much less promising. Most of us are outside the even the 1 Sigma limit. I think we're down to probably only a few % probability of seeing anything happen here, but it's a possible one. It's also, I think, fainter.
Rick, Kevin here. Can you explain the colors on your last colored map of center line,
Sure.
shadow lines, and sigma lines, please?
Yeah. Can you see my mouse?
Right now, yes, we can see your mouse.
Okay, so this is the center line. It's supposed to be green, but I've messed with it. So that's the center line of the predicted path. And the 2 blue lines are the predicted edges of the path. So in theory, if you're just outside these blue lines, you won't see anything. However, they don't know the exact path of the asteroid, or I suppose, well, they probably know the star well enough. But anyway, so then there's a 1 Sigma error possible in the path. and that extends out to the red lines. So that means there's a 69% probability that the real path will be between the two red lines. So anywhere within between the red lines, you've got a significant chance of seeing the occultation. And that's all I have. Any questions?
Awesome job, Rick.
Thank you.
Thank you. Very good. Apparently the 2022 handbooks are out. I haven't seen them yet, but they are supposed to be being sent out to members.
Kevin posted, I posted in the chat David Turner's topic of his speech.
And
Has
I believe-
anyone seen a handbook yet?
No,
Okay.
it's coming. And Downtown posted the link for the auction for Focus Scientific, the bankruptcy sale.
Just one comment on the auction sale. I noticed, I mean, if you look at the opening bids, a lot of them are really spectacular. You can get some fabulous deals if they don't go up too much. But one thing to be aware of is there is a 15% service charge and 13% GST on top of whatever you bid. So that's a fairly significant increase if you're looking at one of the more expensive items.
So Rick, Kevin here, you've gone through the auction site. Does it sound like they've moved everything from Ottawa to the Toronto auctioneer? That's what I got out of it.
Yeah, I didn't notice.
Pick up in Toronto, and that there were only about 199 items listed. That seems like not nearly enough.
Yeah.
Okay.
Okay, so our next meeting is on December 8th. And at 7 p.m. it'll be on Zoom and we'll be live on YouTube for that. And we do have our weekly socials that we hold on Wednesday nights, and that email link will be sent out to our chat list. So if new members are not on our email list, contact us and we'll get you all set up so you can get these, get the links and get to chat with the rest of the folks in Kingston. And if you're not a member and you're watching and you'd like to become a member of the Kingston Center, you can go to the RASC store and sign up. You get the Observer's Handbook, the electronic copy of the Journal of the RASC. There's observation programs. You get a copy of Sky News, regular Kingston Center newsletter, and our local email list. A lot of fun. And of course, we have our library, and the library list is online. So I think with that, we can say goodnight to our folks on YouTube, and we shall sit back here and